answered. All right, let's switch over to the book. See some book questions. Start with this one right here, number 18. I may or may not have assigned this. I probably assigned this earlier. That's a pretty classic question right here. We got a steel ball. We'll just do it straight from the book. 3 kilogram steel ball strikes a massive wall at 10 meters per second at an angle of 60 degrees from the wall. It bounces off the wall, boing, with the same speed and angle. Right. Now pause right here. They're helping you out quite a bit here because this is a what kind of collision? Perfectly elastic. How do you know it's perfectly elastic? Because the kinetic energy after is equal to kinetic energy before, because the same speed, right? The ball is in contact with the wall for this tiny time interval, 0.2 seconds. Okay? It's approximately human reaction time. What is the average force exerted by the wall on the ball? You guys solve it. I'll solve this off screen, and I'll see if you guys can beat me to the answer. Beat me to the answer. Right, for the video, I'm going to pause. So if you're watching this at home, pull out some paper. We're going to pause this, and then we'll be back in a moment. All right, recording is resumed. Let's take a look. So do you guys see that the fact this is in 2 dimensions, and we're talking about vector quantities, right? Velocity, momentum, those vector quantities. Maybe you have to break this into X and Y components. I mean, they very conveniently gave you an X axis and a Y axis, right? Now let's think about what stays the same and what changes as a result of the collision. Okay. Now, if you just focus on the Y component of the ball's motion, does that change before and after the collision? No. I mean, the total speed was the same before and after. And in fact, its Y component would be also the same before and after. But what about the X direction? Isn't it true it's headed towards the wall before the collision? It's headed away from the wall after the collision? That is definitely a change of motion, isn't it? Right. What did you guys get for the velocity of the wall? The velocity of the ball headed towards the wall?
Sine 60 times.
Yes, 10 meters per second times sine of 60 degrees, because this is 60 degrees, right? Do you guys see like a right triangle right here? Right. And that comes out to 8.66 meters per second. You guys get that? Right. So that's how fast it was headed strictly towards the wall. Now, if it rebounded, boing, right? And you know, apply the same geometry. Would it be going the same speed but opposite direction away from the wall? Right. Guys, what's the difference between 8 meters per second towards the wall and 8 meters per second away from the wall? What's the difference? Right. So if you have like 8 minus -8, isn't that like 16? Right? And then and change that. So that is like 17.32 would be the change in velocity. Okay, now we're a step closer because here's the impulse formula. Right, force times time interval results in some mass time change in velocity. Okay, we got a change in velocity. Pop it in there. They told you the mass of the ball, and they told you the time of contact during the collision. And it's usually a tiny fraction of a second, and that's true in this case. So can you just divide the time over? And you get 260 newtons. Okay. You guys get that? Okay. How about this? What if, I know that was bouncing off the wall. What if it was bouncing off the ground? Probably do something pretty similar. And I guess what I would change is I would say that would represent the average net force. Because then you have to say, well, the ball has a weight, so maybe it's a greater force from the floor. So that's usually what they do is they say, well, just find average net force. And it's like the same. Right. All right, you guys ready for our next one? Let's do this guy right here. Whoops. Actually, this wraps around. That's okay. I still want to do this though. Right. You guys see the bullet being fired into the block and bullet turns into a projectile? So they gave you some numbers down here. Let's take a look at these numbers. It says a bullet. Not gonna let me. I'll draw this out for you guys too, so you have the numbers to work with. A bullet of mass so many grams. Right, it's fired into a block with mass of so many grams. So I got 8-gram bullet, 250-gram block. The block had been initially at rest, edge of the table. They give you the height, 1 meter, and the bullet remains in the block. And after the impact, the block lands at a distance of 2 meters away from the edge of the table. Determine the initial speed of the bullet. How fast was that bullet fired? You know what? Actually, I want you guys to solve this in terms of variables. Forget the numbers. Just look at that picture. Look at that picture and solve that in terms of variables. how fast was that bullet fired so that it lands at that distance away from that height table? We go back and pause this recording again. Watch this at home. Pause recording. Resume record. All right, recording's rolling again. All right, so take you guys through this since we got a couple minutes to the bell. Okay. Now, I'm going to solve this backwards in time. So I'm going to start with the projectile, like where it landed at distance d, and work my way back to the collision, and then work back in time from there to find the speed of the bullet, which is the question. Right. So couldn't you guys say that the distance that it goes is equal to the post-collision speed times the time of fall? Right. So I do v post. Now this is not the speed of the bullet. This is the speed of the collision post collision, right? Right, which is slower than the speed of the bullet. Right. But what is the time of fall? Doesn't the time of fall have to do with the height of fall? Right. So then the height of fall, well, that's 1/2 gt squared. Hey, isn't this what you would learn in college? Right. 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 So couldn't you solve for that time of fall based on the height of fall? Right. Does this look familiar? Right. Say if you do the shaft is 125 meters tall, you say, oh, I've been falling for 5 seconds. Kind of like, and then take that time in terms of the height of fall and substitute it into that t, and then you can get the distance that it would landed as a function of the height of fall and the post-collision velocity, and also the gravity field. Okay? Guys, that? Right. That's all the projectile stuff. Oh, and then what is that v post-collision then? V post-collision is this right here. You just take this square root and divide it down. Well, flip, multiply, right? Right. Okay, so there you go. Here's after the bullet collides with the block, how fast the two would have taken off together, based on where the block landed and how high the table was, of course, the planet that you're on, right? Right, guess that? Actually, so some good questions would be like, what if you switch planets? Like, how would that, switch like something? Okay, but continuing on down here. There was a collision that led to this in the first place that involves conservation of momentum. In fact, it's perfectly inelastic collision. Isn't this perfectly inelastic? Mass times velocity of the bullet is equal to some of the masses when they're stuck together. The bullet embeds in the block times the post-collision velocity. Okay? And post-collision velocity, well, that's what we did all this projectile stuff for. That's this expression right here. Just substitute that in right there, right? And then when you do that, it looks like one thing you have to do is divide down the mass of the bullet. There you go. The firing speed of the bullet is the combined masses divided by the mass of the bullet, all multiplied by this expression, which represents the post-collision velocity. Okay, there you go. This is how you can figure out the firing speed of the bullet if you know all those other variables. All right. So tomorrow we'll do some FRQs. You guys remember by this Friday have the AP Classroom Unit 5 done, and then we'll go over that on Friday. Yeah.